Wonderful, thank you. Just let me share my screen here and I can start the talk. So, as was mentioned in the introduction, I am going to be talking about a variation of the gradient boosting regression algorithm inspired by a problem related to the sort of noise and potential outliers in data known as heteroscedasticity. So I'll start the talk by talking about this problem of heteroscedastic noise in the data. I'll give some sort of theoretical positioning about how thinking about this problem in specific ways maybe changes the way we write some of the fundamental algorithms of machine learning. That will inspire the algorithm design and variation, and then I will run through some experimental results using synthetic data generated to have different types of heteroscedastic noise in the target variable. So, as I'm sure everyone in this room is aware, one of the core assumptions of machine learning is that we have some kind of underlying relationship between the features that we have collected and the target variable we're trying to predict. So we need that in the data for the model to be able to learn something. But in most real-world problems, the relationship between the features and the target variable are either underdetermined, meaning that we don't have either all of the features and data points we need to perfectly to predict it, either because we don't know what they are or we can't measure them, or because the data is in itself, in some sense, fundamentally noisy. And in practice, often it's difficult to tell the difference between these two, and perhaps they always both occur. So, heteroscedastic noise means we're thinking that even though most data sets contain some noise, and arguably all data sets contain noise, in certain problems, that noise could be coming from a variable distribution across the problem space. So typically, as I'll show very shortly, we assume that noise comes from a fixed distribution, but there's nothing preventing the noise varying across the types of records that we're trying to make predictions on. So that's what we refer to as heteroscedasticity, when either the mean or variance or both of the noise is varying across the problem space. So let's kind of put that into a mathematical framework. The standard view, this is the really simple view of what the relationship in the data is that we're trying to make predictions about, where each record yi of the target variable we're trying to predict is determined by some underlying fundamental relationship f star that's a function of our feature vector xi plus epsilon I, which is the noise for that specific record. And typically it'll be written that epsilon I comes from a standard fixed distribution, usually a normal distribution, but could be something else, but that the parameters of that distribution are fixed. Now, when we start to consider heteroscedasticity, what we're going to be saying is, well, actually, that epsilon noise record is no longer just drawn from that fixed distribution. Instead, it's some function of a varying parameter space, and in this work we're going to additionally assume that the parameters of that noise distribution can be predicted from the features, i.e. that there's factors of the feature space of the problem that will reveal something about the nature of the underlying noise. So the next thing to think about is, okay, how does that relate to our machine learning models? So the standard picture of a machine learning model is that we have some function f hat, which is tunable by modifying its parameters, and that by feeding the feature vector xi into that function, we will get an estimate of yi, which we call y hat I. Now, fundamental to understanding that performance of that model is the error. So regardless of what kind of loss function we use, whether we square it or we take the mean absolute error of it, the error fundamentally is the difference between our target variable and our predicted variable. Now, that error, we can use the nature of that error to do a decomposition of what we see with that heteroscedastic noise and actually group the terms together. So we can say, actually, the model's ability, the difference between that underlying f star of xi and our estimate of it, f hat, produced by the model, is one source of error, arguably saying how well does the model capture the true underlying relationship. plus the error that's inherent to the problem, which here we're using that heteroscedastic noise function. So now we have kind of two components to that error. And in fact, the way a lot of machine learning approaches try and deal with the heteroscedastic noise problem is that this latter term here, they will try and learn the nature of that noise distribution and incorporate that into the loss function somehow. So that requires you, of course, to be able to model that noise. And so you have to have some way of determining which elements of the data points you have tend to be noisy versus those that are not. There's many different sort of domain-specific applications of that, but in general, you're trying to do that separate from the learning problem. However, what we're proposing in this work is that actually, once you think about some of the fundamental ways that the gradient boosting algorithm tries to improve its learning process, it suggests an alternative way to adapt to this heteroscedastic noise. So, quick review of gradient boosting. The core idea is that you're going to build up a model from simpler components as an iteratively constructed ensemble. Like many other ensemble methods, that's not different. But the difference with gradient boosting is that each new model in the ensemble is attempting to correct the residual error of the previous model. So that goes back to that previous slide I showed. This notion of the error is also referred to as the residuals, basically the difference between what you've been able to predict so far and what the actual value is the residual. And the subsequent models in a gradient boosting ensemble are attempting to predict those residuals and add them into the ensemble. So the presence of noise, it's been known for a while, can lead to the boosting process to overfit. So early boosting algorithms suffered from this quite poorly, attempting basically to fit the noise. However, modern gradient boosting algorithms have less of a problem with this, but of course that's achieved through regularization, meaning that in some sense which forces you to learn a simpler model in situations where there's too much noise. But what we're arguing in this paper is that heteroscedastic noise presents an opportunity because that noise is not evenly distributed across the problem space. So regularization in some sense is a blunt instrument because you're only trying to reduce the complexity of the model across the whole problem space. But ideally, you would only reduce the complexity in regions of the problem space where there's higher noise. So that's the core insight of the model. The basic algorithm we're proposing is as follows. As just like with a standard gradient boosted model, train a base model and calculate the residuals. Now, before you train the additional models in the ensemble, we're going to label the training points by identifying the residuals that are below a certain threshold of noise. We use a z-score normalization of the residuals, and we say those are low noise points, meaning that we think that we should continue to include them. We build a classifier at that point to determine whether a data point is going to be low noise or not, and then we only fit the residual regression model on those low noise points. Now, initially we start with a fairly high threshold of that z-score normalized, so most data is included in the initial boosting layers, but that gets gradually lowered. So as you get deeper into the ensemble, you're excluding more and more of the data points with the kind of core idea that they're potentially just suffering from noise that's fundamental as opposed to error that's that derived from the inability of the model to predict that fundamental relationship. So at scoring time, it's a similar process. We start with the base model prediction, but through each layer of the boosting, we're going to predict the probability that each data point is low noise, and then the residual error expected at that point. But we're going to attenuate the boosting of those residual corrections using the probability values. So what this looks like as a formula is as follows. As I mentioned before, we start with a base model prediction b hat of xi. Then we've got a negative sum over all of the m layers of our boosting algorithm, where we've got the probability that the data point is low noise multiplied by the prediction of the residuals at the jth depth into that boosting process. So in a standard gradient boosting algorithm implementation, There will be a sort of an attenuating factor that impacts how much of the residual correction you include, but it's a fixed parameter across all depths of the boosting algorithm. So what we're and it's applied sort of uniformly across all points. Whereas now we've got an attenuation factor that both depends on the actual record itself, and it varies as you move through the layers of the gradient boosting. So the core idea is where the residual model is only applicable for low noise data points, so it's appropriate to try and predict whether we think the data at that point is low noise or not. So that's the core idea. We've implemented this as a standard scikit-learn meta learner. So you can basically import it as is shown here and you'll need a base learner both as a classifier and a regressor for the internals to the model. You instantiate it telling it what you want to use as that classifier and regressor, and then fit it using the standard sklearn type interface. So that's available as a PyPy package and an open source library. In order to evaluate it, we decided to generate synthetic data sets with varying levels of heteroscedastic noise because we wanted to understand what types of heteroscedasticity the model adapted to, and we also wanted to know what proportion of the time it appeared to work compared to sort of alternative approaches. So what we did was several multiple variables that were changed in order to vary the size of the data set for testing. So here you see the number of features inputted as well as the total number of records, the proportion of records that are drawn from a larger, noisier distribution. And then what's not shown here is that we generate two functions, one that takes first of all, the features to the model are generated drawn from a set of random distributions. And then we generate random functions that predict the target variable, that's that f star function from earlier slides, that are combinations of linear and non-linear combinations of those feature vectors with also random transformation. So basically sort of random functions. We create an additional random function that will determine whether the point a given record belongs to the low noise or region of the space or not, and that is effectively just a random logistic function, and then we adjust the threshold until it meets the required outlier proportion here, and then we use a standard deviation multiplier. So in this particular work, the heteroscedasticity is only applied to the variance. So basically, if you're in a higher noise region, you've got a much larger standard deviation. We repeat this process, generating 100 different data sets for every combination of these parameters, and then evaluate multiple models on their ability to predict those random functions. So we use for the evaluation, we decided to use both two standard gradient boosting implementations, the one that comes in scikit-learn, as well as the light GBM, which is a very multi-purpose, powerful GBM implementation. The OAGRE model is created with two different base learners, with decision trees, but also with extra trees. And we also look at using those sort of base learners as well, extra trees and decision trees. Oh, I just noticed that those parameters are the wrong way around. That should be 200 there and 20 there. So the idea with that is we want to know the model has to be able to beat the simple models, the kind of the naive models. Otherwise, it's not adding any value, and it has to be able to beat the standard GBM implementations. Otherwise, this approach to heteroscedasticity is also not added anything. So that's the comparison set, and then for performance, we looked at both the mean squared error on a 10% holdout set for every one of those synthetically generated data sets. And then we're looking at the number of times that a model wins in that competition. And then when it does win, what's the average percentage improvement or reduction in the mean squared error. So the first big surprise was that the scikit-learn GBM implementation was performed very well on this task, outperforming light GBM. But then the OAGRE implementations, both of which outperformed light GBM in terms of number of wins, although sort of only marginally with the decision tree version. But so collectively, they got to the point of about 30%, winning 30% of the time. And that when they did win, their improvement was somewhere between sort of 7 to 12%. So non-trivial improvement in the model, a non-trivial number of times, and they sort of vastly outperformed the number of wins of those naive base models. So we take that kind of, see the first kind of observations I'll just outline again there. Strong performance in terms of proportion of wins, outperforming light GBM on this task. The average improvement over the next best model is in the range 7 to 12%, and that 30% is certainly a useful proportion of the time for the algorithm to be the best model. We also wanted to understand, as I mentioned earlier, what was the nature of the heteroscedasticity that led to the performance for the OAGRE model to outperform. We analyzed those random functions that were generated in each of these synthetic data sets using multiple different ways of breaking down the data. The pattern that stood out the most was when we looked at the proportion of terms in those random functions that were nonlinear. So on the x-axis of this plot, you see as increasing proportion of those terms are nonlinear, the likelihood of OAGRE winning increases. So there appears to be sort of a general trend upward to the left there. It appears that nonlinearity is one of the determinants of whether the OAGRE model is likely to outperform the alternatives. So, conclusions. By going through this process of considering what heteroscedastic noise means to the underlying problem a model is trying to solve, it prompted us to go through this exercise of thinking about a variation of the gradient boosting algorithm, exploiting the fact that the gradient boosting algorithm tries to continuously fit residuals so that we could change it to attenuate the inclusion of those residual predictions based on this idea that not all regions of the space, when you're dealing with heteroscedasticity, have equal amounts of noise. Our experimentation indicated that it could add value in approximately 30% of problems with heteroscedastic noise. So our recommendation would be, if you're sort of targeting and trying to build models in this space where you're suspecting the presence of heteroscedastic noise, it's worthwhile including in the candidate set of models because you can see from the previous results that the potential improvement is non-trivial. Thank you for your time. As I mentioned before, all of the code is available on GitHub as well as GitHub, and as well as the package being available on PyPy. You can find my GitHub IO page here with sort of additional projects I'm working on, and how to get in contact with me. And I have a book out on getting data science done. Always happy to get feedback and talk about that. Thank you for your time.